Thank you very much and good evening. First of all, my best wishes for the happy Chinese New Year. Kung Hei Fat Choi. What I'd like to do is there's quite a lot of stuff in this, so I'd like to zip through the slides, and if you can make a note of the bits of items that are of particular interest to you, we can have a good questions and answers session at the end. So, I'm going to treat you exactly the way I treat my students at Salford University. So in order to find out which way to go, we need to know where we came from and understand all the lessons learned in the past. Ladies and gentlemen, it's 11 decades of commercial air transport in 2 minutes. Started with airships, which came and went. Biplane airliners came and went. Flying boats came and went. Piston props came and went. Turboprops came, and they have gone for long distance transport, but they, of course, we use them for commuting purposes. Turbojets came and went. And the idea is why not use the best features of a turbojet with a shrouded propeller, a turbofan, and that gave birth to the fan jets. And this aircraft went into service the year I was born, 1958. We are learning a bit more about the atmosphere, so let's just have a very, very quick look at the atmospheric properties. What we got is, if I can find my laser pointer, bear with me 1 minute. We have the variation of temperature with altitude. I was born in Sri Lanka. What I didn't realize is that at high altitude, the air over the tropics is actually colder than the air over the polar regions. Anyway, one of the things you want to look for is to maximize the efficiency of an airliner, is to maximize the difference between the ambient air temperature and the combustion temperature. And it was with these things in mind that we do a little bit of theory. I promise you, this is the only equation you'll find in the whole slide. That equation on the top indicates how heavy, how big, how high you should fly, and how fast you should fly. And the magic number that holds the whole thing together is this thing called the lift coefficient. It takes me about 2 years to train my students to figure out what that number is, because what matters is this lift over drag ratio. And for me, the first aircraft or airline, I should say, that captured my imagination was the Boeing 747, able to use existing runways to some extent, although they had to be elongated to 3 kilometers. But my God, what a fabulously successful project it is. It's been on continuous production for 42 years. And the backlog is that it looks like it's going to be in production for another 10 years at least. In fact, there is one time where the whole aircraft is kitted out as a laser gun to shoot down ballistic missiles. So, what exactly is the problem? The bigger the plane, the flimsier it becomes, the more it bends and twists. So we have structural distortion problems. By the time I entered the scene, we started using computers to control the aircraft. And by relaxing the stability, you could get better cruise efficiency. When I returned to the university, mainly for my own benefit, I set some classroom exercises so that the students would be able to try and get the best of both worlds and use new materials and come up with something that is most efficient for a global transportation system. Now, don't worry too much about the next slide, but this is the actual solution to that problem. But what's interesting is the last set of numbers the students came up with, if they did the sums right, those numbers are remarkably close to what eventually became the Airbus A380. Very, very close. So, what were Airbus doing at that time? Well, in 1990, I did not know this at that time, but they were actually working on this project. Now, Airbus and Boeing will claim that they do not know each other. Don't you believe them? They did have an affair in 1992, but it didn't last long. In 1994, McDonnell Douglas came up with an aircraft aircraft design that looked remarkably like the A380, but unfortunately they went down under, which paved the way for Airbus to go it alone. And so, what exactly was the problem? Well, it's the sheer scale of the solutions that we are coming up with. The length of the aircraft remained about the same for the given configuration, but it's the wing area. That black line is the outline of a Boeing 747. Its wing area is about 520 square meters. The particular, the A380 one is about 825 square meters. That's a huge increase. And that was going to bring on an awful lot of flexural problems. The wings were going to bend and twist all over the place. The question is, can you control this using new technologies? Also, to give another perspective, the root chord of the A380 wing is larger than the length of the single aisle wing. So these are the numbers that you see in a shipyard rather than an aircraft factory. Well, a three-dimensional mock-up. When I'm at the Broughton factory, with my height, when I stand at the bottom skin, at the root end, I can't reach the upper skin at the thicker section. But of course, it quickly thins down as you go along the span. By the way, just for information, the air cycle machines or air conditioning packs are housed in the leading edge of the root section of the wing. Question is, do we want this particular type of aircraft? The answer was definitely yes. It turns out that regardless of gigantic economic collapses, wars, natural disasters, whatever, the world air traffic doubles every 15 years. And we can't go on building new runways, new airports all the time. And therefore, it was the answer was that yes, go ahead. We need this aircraft. So there's another problem concerning the environmental issues is the combustion temperature. As a general rule, if you burn the kerosene at a low temperature, you find that you run into problems with carbon and carbon oxides. Nitrogen takes over the problem at higher temperature. So for this reason, it was decided to set the burn temperature at about 1650 Celsius, whereby they thought you could get the best of both worlds, and also you had to worry about volatile and organic compounds as well. Noise, for certification purposes, you place a microphone about 2 kilometers upstream of the touchdown point, another microphone about 6.5 kilometers from the brake release point for takeoff calculations, and then third one about 0.5 kilometer on the offset from the runway. It's that microphone that will register the greatest noise because the engines are at full throttle. Now, if you look at the certification, for 4-engined aircraft, you're allowed something like 105 decibels. I'm pleased to say that the A380 is a very, very quiet aircraft. It's only 96. EPNB stands for air perceived noise in decibels, and we always reference it to 20 micropascal. That's something that's never mentioned when you read the general text. What about the engine itself? This is a Trent 900. First of all, it's about a third bigger than the RB211, which powers the 747. The Trent 900 is not a Trent engine. The 500, 600, 700, 800 basically share the same aerodynamics. Trent 900 has got swept fan blades. The leading edge is bent, if you like. It's a different set of aerodynamics. At full tilt, each blade, the fan blade, its tensile force equates to hanging 90 cars. And the airflow is about 1.2 tons per second. The tips go supersonic, and the high pressure spool rotates in the opposite direction. BPR is bypass ratio. For every kilogram that goes through the combustion chamber, 8.2 kilograms goes on the outside. That's where a majority of the thrust actually comes from. Overall pressure ratio, just for comparison, those who drive diesel cars, your compression ratio is about 21, 22 to 1. Petrol even lower. This one, the compression ratio is twice that of a diesel car. And staging, don't worry too much about it. I just want you to note that number. Is the intermediate pressure compressor has got 8 stages, and the turbine has a single stage. So that turbine is driving 8 stages of compression at the intermediate shaft level, and the sea level static thrust is about 31 tons, sorry. By the way, that's my wife standing there. She's seen many of these RB211s. She's a librarian, cultured lady seated over there. And her first words on seeing the Trent 900 were, "My God, he's a big bugger." The alternative engine is the American engine. It runs slower than the Rolls-Royce engine, but works harder. Its bypass ratio and the overall pressure ratios are a bit higher, but it's a two-spool engine, and both spools rotate in the opposite direction to the Rolls-Royce fans, because Americans have to be different. You do as many tests as possible on the ground, but there are certain tests you have to do it at altitude and at the right Mach number, and for that reason, the only way to do that is to attach it to an existing aircraft. And the biggest problem here was the ground clearance. That engine is about twice the diameter of the CFM56, which powers the A340 test bed. I thought I'll throw this in. In addition to the main engines, which equates to about 80,000 shaft horsepower, at the very back, at the tail cone of the aircraft, you have a fifth engine which is used to run the auxiliaries. It so happens that the power output of that engine equates to the Merlin engine that powered the four-bladed Spitfire. That is what it takes to keep 440 passengers cool, maybe 500 passengers happy. New materials, it is predominantly a metallic aircraft, but the whole of the back end is non-metallic, so is the center section of the wing. The bits in yellow are a combination of the two. It's a hybrid material. It's aluminium sheets pasted onto glass fiber mats, and that particular material was developed mainly by Delft University in Holland. We're still not sure whether it's the right thing to do, but hopefully, according to theory anyway, you should hopefully get the best of both worlds in terms of corrosion prevention, minimum maintenance, adequate strength, and so on. I had to show this, otherwise my bosses will kill me. These are some of the projects done by my students and colleagues. Lena, she got a PhD out of this, structural stressing. Perasith from Thailand, he's now works for Thai Airways, did a lot of the stuff on fin and rudder sizing. By the way, that fin is about 25% less than what it was originally, and we had a part to play in that. Engine throttling simulation by Cameron. Cameron is now working on A380 undercarriage systems. Christopher won the Frank Little Trophy on doing some aerodynamic studies on pilot flow interaction, and he worked for Rolls-Royce after graduation. One of my colleagues did some work on separation distances, and Christophe from France, very good at mathematics, did some work on feedback control for load alleviation. So the Salford bits are here in green. Everything we did is symmetric mode. That means everything that happens on the port side is exactly mirror imaged on the starboard side. Germans did the asymmetric cases, and when you integrate the whole system, you want to make sure that one system does not end up fighting the other. So for that reason, this particular box of tricks makes sure that everything is phased in and out instead of jerking the passengers all the time. And once all that is going on, what you don't want is for the aircraft itself to get into an unusual mode. So the flight envelope protector, it keeps an eye on things. If by chance the aircraft is beginning to approach an unusual attitude into a flight upset condition, it basically asks the transient limiter to back off, and it goes back into control mode, and then they can resume the normal functions. You got 3 primary and 3 secondary computers, and normally you have the managing director who sits at the top, and if by chance things begin to go wrong, you then hand over control to other bits and pieces. Let's just quickly find out what they are. When everything works, a teenager can fly this plane. If by chance things begin to fail, you find that you begin to start losing a little bit of protection. But if you lose all 3 primaries, the secondaries will start running the show. And even if you lose all 6, you are not at zero survival situation. What it will do is enable you to hold her steady and level and buy you time to reboot at least one of the 6 digital computers. Final settings, 560 tons all-up mass. By the way, pressurization involves pumping into the cabin 1 ton of air. It equates to 10 passengers. That is what it takes to keep the passengers alive in an A380. You also have about half a ton of paint, grand total of about 68,000 gallons, and it can fly for about 16 hours with a full payload. And these are 19,000 hard landings. If you do 3 hard landings a day, it can absorb the punishment for 19 years. And it's can stay airborne for up to a maximum of 16 years or 25 calendar years. Sorry, when I say airborne, 25 calendar years is the lifespan. After that, the chemistry of the materials is unknown. The taxiway width, what you want is the outboard engines to stay above tarmac, otherwise these things will start sucking in all sorts of bits and pieces, including rabbits and rats and God knows what. So ideally, the width should be about 60 meters plus about 7.5 meters of hard shoulder on either side. With 75 meters, meter wide runway or taxiway, you're able to do a U-turn. Flight deck is pretty much the same as any other aircraft, any other Airbus airliner, except some 1 or 2 additional items. This additional display in the corner contains information on airports and so on. It effectively replaces the maps and so on which you have to carry. It also does not have pitch trim controls. They're all electronic. You have the pitch trim and the rudder trim in there instead of the wheels that you normally see in the other Airbus airliners. You also have loudspeakers. I've never seen loudspeakers on the dashboard before. But having spoken to some of the pilots, apparently it's a very good thing. Otherwise, they had to keep the earpiece, the headphones all the time. And ladies and gentlemen, this is an electronic, all-digital cockpit. That is why it has got a printer over here. If you now place that simulation facility on a robotic device called the Stewart platform, which tries to mimic as much of the 6 degrees of freedom as possible, you basically get a full motion flight simulator. And in Airbus's parlance, this is known as aircraft -1. Let's just have a quick look at the systems on board. You have 1 electrical generator per engine. You also have 2 generators at the back end of the aircraft driven by the alternate power unit. In addition to that, I'll see if I can do a juggling act here. On the innermost, this bit here, on the innermost fairing of the flap track, you have a ram air turbine. Of course, we are engineers, we like to be different, so we don't refer to it as a windmill. But that particular ram air turbine, the diameter as it deploys it's about the same as my height, and it generates just minimal electricity, about 70 kilowatt ampere. And in addition to that, you can plug in external power as well. And this thing surprised me. There are 4 batteries on board the plane, 3 at the nose section and 1 near the tail section. The capacity of that battery is the same as that in your car. That's it. That's all you got. It's just there to start the APU, alternate power unit. Hydraulics. It's a high pressure system, 5,000 psi. It's got 2 circuits. Normally you have 3 or 4, but the reason you have only 2 is that part of the work is done by electrical actuators. This is your standard. It is predominantly, at the moment anyway, is a conventional hydraulic actuated aircraft. You also have electro-hydrostatic actuators. Some people claim that this is brand new technology. It is not. The Vulcan bomber had it 50 years ago. So you got the electro-hydrostatic actuators. You also have electrical backup hydraulic actuators, which are new. It is effectively a conventional actuator, but with its own pump built in. So if by chance you lose pressure in the circuit, it has its own reservoir and it can act as an independent system. You also have a DC motor. I could not find out what voltage it was on, but anyway, I'm hoping to do that later. The most important part of this aircraft from a control point of view, the bit you do not want to lose, is this tailplane, variable incident tailplane. That has got 3 independent systems, 2 hydraulic systems and a DC motor. I'm also very particular, much more particular about the leading edge of the wing, this high lift devices, rather than the trailing edge. If you lose that, at least according to theory, I had to be very careful because at least there are at least 2 test pilots in the audience. If you lose that, you are in dire straits. Whereas trailing edge devices, you can get away with it to some extent. So leading edges have more redundancy, and then you've got hydraulic motors, and the rudders have got 2 electrical backups per control surface. And finally, the spoilers. That's the other thing. The numbering system varies according to which supplier you're talking to. Engine people do the numbering from port to starboard, so it goes 1, 2, 3, 4. In the case of spoilers, it goes port 1, starboard 1, port 2, starboard 2. It's like football scores. Tire manufacturers go by axle. So it goes wing landing gear axle first, 1, 2, 3, 4. Then the rear axle for the wing landing gear, 5, 6, 7, 8, and so on. So when they say tire number 17, you have to think which one it is. Just make a note of this. The spoilers 5 and 6 are the most important of the 8. There's something very special about because of the way they control the bending and the flexing of the wing. When everything is normal, it is primarily a hydraulic aircraft. But if by chance you lose one of the hydraulic circuits or one of the engines starts playing up, it will start energizing the electrical actuation systems. If by chance all the engines start playing up, then the auxiliary power unit will cut in and start pressurizing the emergency hydraulic and the DC motors. If by chance you lose a whole lot, then you have this the windmill that pops out, the ram air turbine, and the only thing is you are now using that energy purely to power the onboard computers, nothing else. You're effectively a glider. You also have a few other features, so I'll skip that bit, I think. The only thing to remember is that the passenger doors are electric, so they are operable by even the smallest member of the cabin crew. And also the aircraft, the engine thrust reversers are electric as well. As far as I know, there is no other aircraft powered by electric thrust reversers. They're either hydraulic or pneumatic. So you construct a circuit diagram, hooking up all the bits and pieces. If you then get hold of all the hardware and lay them on the laboratory floor, this is what you'll see. This is in Toulouse. Buried in there is a complete A380 hardware system, and we are standing on a balcony, so we're looking down on this is known as the Iron Bird facility. Behind us is the full motion flight simulator, the aircraft -1. In Airbus's parlance, if you hook up the aircraft -1 to the Iron Bird, as the pilots fly the plane, you can see how all the switchgear is cutting in and out, and that is referred to as aircraft 0. And that is where you do all your dress rehearsals before every single test flight. You also have a cabin 0. Remember, they had never built a double-decker before, so they want to make sure that they got that right. And also you have a fuselage 0 to do all your pressurization testing. How am I doing for time? Okay. Right, let's start building the plane. You start building it with the center wing box. This bit here. That is French. Rib number 1 is French. Rib number 1 is the one that joins the center wing box to the rest of the wing. This is the first wing coming off the production line at Broughton. The first pair of wings, I'm afraid, will never fly. and you have to break them. The reason is you want to make sure it is failing at the point you predicted that it will. So you have all these fancy jacks. The wingtips deflect by about 25 feet, and you also have lots and lots of strain gauges just to make sure that it is bending and twisting the way you expected it to. The second pair of wings will also be punished, but not broken. This one is in Germany. What you're trying to do is mimic the flight loads for typical sorties, and you got all sorts of hydraulic jacks to try and simulate a 16-hour flight in about 11 minutes. That's the same level of punishment. It's not perfect, but it does the job fairly well. Cross-section of the fuselage in Germany. Cargo deck, main deck, and the upper deck. Again, mainly, depending on the section, it's that bed that is a hybrid. It's known as glare. It's a sandwich of aluminium and glass fiber. And also the upper deck, the main beam, is non-metallic. It's fiber-based composite. So there are lots and lots of innovations in this aircraft. This is the first aircraft, the manufacturer serial number 002, nearing completion. There's one type of test for which you need the complete aircraft, and that's a vibration test, the ground vibration test. This is not the first aircraft that was to fly, because you had to conduct some oscillation tests, and that's typical of the sort of shaker we use. I used to love doing these when I was a postgrad. We had these actuators basically vibrate the whole structure at prescribed frequencies and amplitudes, and to pick up the outputs, we use these accelerometers. These are tiny devices which I got piezoelectric crystals, and the idea is that as they compress and expand, they generate a charge in coulombs, which is what you're picking up. And what we're trying to do is make sure that it's vibrating the way you thought it was going to shake. And also, it takes about 6 weeks of testing to get all the results. This is the actual aircraft undergoing testing. I thought I'll throw this in because the bits in red are the items, compartments which hold the slide rafts. For the main deck, the slide rafts are at the bottom of the doorway, whereas for the upper deck, they're actually below the doorway. This is to make sure that the drop isn't too much when you ditch on water. But for me, the most fascinating one is this one here, the belly of the aircraft. That, on deployment, creates a balcony walkway with a slide facing backwards. Now, what are the conditions? Well, I'll let you read this for about a couple of minutes. Those are the conditions that have to be met when you conduct an evacuation trial. So, I'm delighted to say that all 873 human beings exited the aircraft. However, there was one passenger who did break his leg. It's quite a dangerous test during this trial, and this is the scene after the evacuation. All the chutes are deployed nicely, and that's the center one I was talking about, the balcony walkway with the slide pointing backwards. However, this one is not a raft. So if you have to ditch on water, that particular slide is not allowed to deploy, and this is reflected in the instructions given to the cabin, the passengers in the safety card. As you can see, that door remains locked. There's no diagram, there's no raft coming out of that diagram. Whilst all this is going on, you have got the MSN 001, which is going to make the maiden flight. The test pilots are doing their dress rehearsals. They actually wear parachutes and helmets, so you never know what's going to happen. And the defining moment came in April 2005. I'll just spend a little bit of time on this. I get my students to plot this in the final year. This is an indication of how high the aircraft can fly and how fast it can fly. And there are maximum and minimum zones. For the maiden flight, you stay well away from the forbidden zones. You don't take a chance. So maiden flight takes place somewhere here, and then over the next several months, years perhaps, you try and keep on pushing the envelope. And one of the borders you do cross is this stall. There is an awful lot of stall tests on the A380, so you momentarily go into that region, but of course you know how to recover, so you come back in. You can't get up there anyway, this is engine limited, but this boundary is forbidden. In fact, the aircraft shakes so much that you just go near it and then you keep on extrapolating and you try and make sure that the aircraft limits are fairly well known at that point. Ground connections, you want to make sure that she's a big aircraft, but she also needs more vehicles to position around her. For me, the most fascinating one is this catering truck, which has to raise itself to the upper deck. And God knows how they keep it stable on a windy day. You also want to make sure that this air bridge, which is reaching out to the doorway on the upper deck above the wing, the superstructure of the mechanism does not tangle with the airframe itself. So nothing beats actual testing instead of doing endless analysis. You know, fully trust your calculations. Wheels and tyres. All wheels have these fusible plugs. If by chance the air inside gets too hot or the wheels get too hot, the idea is that instead of the tyre exploding, these things will melt and let the air out gradually. And of course, your car tyre is typically inflated to about 3 times the atmospheric pressure, maybe 4. These things are inflated about 14 times the atmospheric pressure. Also, no one can beat the tyre manufacturers when it comes to mixing units of measurements in their product specification codes. What this means is the 1270 and 530 are the diameter and the width of the tyre in millimeters. R is radial ply construction, and 23 is the diameter of the wheel in inches, just to make life really exciting. And if you use the aircraft in accordance with the manufacturer's instructions, you should hopefully get about 300 landings at the typical landing speeds. In addition to all the other tests, you also do this particular test, this VMU, minimum unstick test. Alan Foster and Alistair McDicken will be very familiar with these things. What you do is you attach a tail skid and you pull back on the stick prematurely. At this point in time, the aircraft has got enough aerodynamic force on the tail end to get her to rear up, but not enough lift on the wings to get off the ground. And what you're looking for is to try and work out the speeds at which this is happening. And what should have happened next is that you can see the wing landing gear is airborne, so it's the nose landing gear. She's riding on the body landing gear at the moment. What should have happened is she should have just lifted off gently. Instead, they got the sum slightly wrong, and the aircraft pivoted about the skid and started scraping the tail. There was a fair bit of damage, but things were repaired, lessons learned, and that problem was sorted out fairly quickly. Brakes, you've got 5 discs per wheel, and they're non-ventilated, unlike the ones in your car. They'll deform too much. Despite what they say, even carbon brakes do lose a lot of the efficiency when they become very hot. Worst case scenario is not rejected takeoff. It is a flapless landing. When you do the sums, half mv squared, you find that that number turns out to be, because you're squaring the velocity, that number, that particular test is not carried out on the aircraft itself, it's carried out by the undercarriage manufacturers. But the rejected takeoff test is carried out, we'll come to that on the next slide. But the typical temperature you're looking at is about 500 Celsius on landing. And then you have the fancy control systems which will try and make sure that there isn't too much structural damage when you apply maximum braking. This is the rejected takeoff test. What you do is load the aircraft to maximum takeoff weight, accelerate the aircraft to about 166 knots, and then without the use of thrust reversers, you bring the aircraft to a halt using just the aerodynamic surface and wheel brakes only. And the worst thing is that, and this is where I feel very sorry for the pilots, they just had to sit there for 5 minutes whilst these tyres are burning right underneath these tanks full of fuel. They just have to trust that the engineers have got their sums right. The idea is that it's deemed that it will take 5 minutes for the fire brigade to reach the aircraft after an emergency. And also, by the way, the body landing has got 3 axles. The rearmost axle does not have brake packs fitted for the current model. So there are only 16 brake packs in the main landing gear here. So 5 A380s took part in the certification trials over about 1.5 years, went all over the world, plenty of flying, and perhaps one of the most spectacular crosswind landings was at Keflavik in Iceland. It's claimed that the crabbing was so much on final approach that the spectators in the terminal could see the far side of the fuselage until the last minute where it aligned with the runway. Lots and lots of stall tests, most impressive, all sorts of, you can think of power on stall, power off stall, asymmetric stall, flaps on stall, slats on stall, you name it, they did the whole shooting match. One occasion they managed to land an A380 at 592 tons, that's a world record. But they're keeping quiet about it because it's likely to be broken again in the not too distant future. In terms of trying to break the navigation systems, one of the most spectacular flights was from Johannesburg to Sydney, flew all the way to the magnetic and the true south poles, and the idea was to, because from the true south pole, no matter which way you look, everywhere is north, and as expected, the navigation system did throw a wobbler, but as soon as I turned left, it came up with a message. It reacquired the coordinates and said, I know where I am, I'll get you home. And I'm delighted to say that this is the first time ever the airworthiness certificate was awarded by the Americans and the Europeans at the same time. Airbus asked me to put this in. This is concerning exhaust emissions, the noise signatures, recyclability of materials after disposal, etc. Apparently she's a very, very green machine, and I understand this was the first aircraft to qualify on ISO 14001 on the first attempt. Harry Nelson, who used to work here, is one of the test pilots, he sent me this, and people like Alan McDick and Alan Foster love to thrill the trials by getting transport aircraft to perform fighter aircraft type maneuvers. This was taken at an air show in South America. So what happened to the 5 test aircraft? 2 of them have been retained by Airbus to develop future derivatives. The one on which you saw the ground vibration test being conducted, apparently a very rich Arabian gentleman has requested for it to be kitted out as a flying palace. The other 2, I think they ended up with Emirates Airlines, but I'm sure the spotters here will correct me. MSN 003 did not take part in the certification trials, but she was the one who was used to test to make sure that she's ready to receive babies, children, disabled people, pets, etc. And today, when the handover takes place, the manufacturer conducts a flight test lasting about 2.5 hours, and then the customers do another 2.5 hours. I understand from the initial delivery of the billets into the factory to change of ownership, it takes about 1.5 years. By the way, they still refer to this as key handover at Toulouse. There is no key, their doors are electric, but I guess tradition dies hard.
Yeah, Boeing does the same thing.
Oh, Boeing does the same thing. Right, okay. What do you get for your money? My wife and I live in a semi-bungalow, and the land area is about 300 square meters. It so happens that is the the floor space of the main deck of the A380. In addition, you get 200 square meters on the upper deck. You also have dedicated toilets for the flight crew, for the pilots. There will be no need for anybody to run up and down the stairway during the flight. There are 2 self-contained floors, each with their own galleys and toilets and so on. And, this is important. You also have the freshwater tanks just here, just behind the center wing box. But you then have the waste tanks just in front of the rear pressure bulkhead. So as you start using the water, it transfers, this is toilet water, weight transfers rearwards, and to compensate for that, to make sure the center of gravity remains in the right place, the fuel is transferred from the tailplane into the wing. And of course there'll be many more opportunities to join the Mile High Club if you wish. What you're going to do is have a quick look inside the aircraft. So we're going to enter the aircraft. This is just a recommendation for give you some ideas of the possibilities of interior decorations as well as furnishings. We are going to enter the aircraft through the frontmost door of the main deck, and as we turn to our right with the flight deck behind us, you'll see the straight stairway. So we're going to go up the stairway and onto the upper deck on the front bed. If you want, you can have a conference area for business folks who want to do some work en route. You can also provide seating for them, 6 abreast seating with plenty of leg room. If you want to see how the peasants are faring in steerage, you can go to the back end of the upper deck, and if you want, you can have a pub right to the back end of the upper deck. What you're now going to do is come down the second stairway, which is a curved stairway. It follows the rear pressure bulkhead onto the main deck. And I understand that the Korean Airlines wanted a corner shop right at the back end of the main deck. If you now go further forwards, you're back in with the economy class. And if you walk further still, it's like crossing the border from Mexico to the United States. One airline offers this individual cabin, and if you're traveling with a partner, you get a bigger cabin. And this Arabian gentleman, this was the proposal at that time. Whether they went ahead with it, I don't know. But he wanted the main deck kitted out as a stateroom to entertain members of the royal family, I guess. I don't think that sort of place setting would be allowed in flight. Which I'll stop at this slide. I just want to go through the timeline. It was about mid-90s when they started dating each other. Most of the weddings took place in 98. Firstborn conceived January 02, achieved fetal stage later that year, and she was born in November 2004. 2 years later, she was the star of the show, came of age, and fledged in April 2005. This is interesting. Within 2 months of the maiden flight, she performed in front of the general public at the Paris Air Show. It's a week-long show, and she flight demonstrated every day, bang on cue. Spare a thought for the engineers who must have worked extremely hard every night to make sure that she was available at the right time. Evacuation trials took place in March 2006, and just before Christmas 2006, she graduated with first-class honors from institutions on both sides of the Atlantic, and started earning her keep in October the following year. And later that year, she repeated her graduation performance with the American engines. Both types are cleared for service worldwide. So what I suggest is we perhaps take a break at this point and continue with the rest afterwards.